The concept that Saturn could float in a bathtub, though fantastical, is grounded in some of the most fundamental principles of physics and planetary science. To understand why this is even a possibility, we must delve into the unique properties of Saturn, particularly its density, and how these characteristics differentiate it from other planets in the solar system. While imagining Saturn in a bathtub is an amusing exercise in thinking about planetary scale and material properties, it also presents an opportunity to explore some of the deeper, more intriguing aspects of planetary composition and the nature of buoyancy in our universe. Saturn is a gas giant, a category of planets that includes Jupiter, Uranus, and Neptune. These planets are primarily composed of hydrogen and helium, the two lightest and most abundant elements in the universe. Saturn, specifically, has an average density of only 0.687 grams per cubic centimeter. To put this in perspective, water has a density of 1 gram per cubic centimeter at standard temperature and pressure. This means that Saturn's average density is less than that of water. If you could somehow find a body of water large enough to contain the entire planet, Saturn would, in theory, float because the density of the water would be greater than that of Saturn itself. This is not an idea grounded in fantasy but one based on the laws of buoyancy, specifically Archimedes' principle, which tells us that an object will float in a fluid if its density is less than that of the fluid. The low density of Saturn is a direct result of its composition. Unlike Earth, which is a terrestrial planet made mostly of rock and metal, Saturn is composed mostly of gases. While Earth's density is about 5.5 grams per cubic centimeter, Saturn's is far lighter due to its gaseous nature. Its outer atmosphere is composed almost entirely of hydrogen, with a smaller amount of helium, and as you descend into the planet, the gases become more compressed due to increasing pressure. However, even at these depths, Saturn remains less dense than water, which makes the scenario of it floating possible in a theoretical sense. Saturn's composition is also part of what makes it so striking in appearance. Its beautiful rings, composed of ice and rock particles, are iconic features, and its atmospheric clouds feature alternating bands of yellow, white, and brown gases. But the planet is not a solid mass. Beneath its stunning exterior, Saturn's internal structure consists mostly of gaseous layers, leading down to a small, dense core that is made primarily of rock and ice. The outer layers, however, are mostly hydrogen and helium, which are so light that they contribute to the planet's overall low density. What's particularly remarkable about Saturn's ability to float is that it doesn't require a perfect bath to achieve this effect. The concept of a bath large enough to accommodate a planet like Saturn is of course an exaggeration, as no body of water on Earth is remotely close to being large enough to hold a planet of Saturn's size. Saturn's equatorial diameter is about 120,536 kilometers, making it more than 9 times the size of Earth. Even if Earth's oceans were somehow expanded, they would not be able to contain a planet of such vast proportions. The volume of water required would be astronomical, quite literally beyond the scale of anything that exists on our planet. This brings us to another fascinating aspect of the idea of Saturn floating: scale. If we were to imagine Saturn placed in such a vast body of water, we would have to consider how the sheer size of the planet would affect the interaction between Saturn and the water. The gravitational pull of Saturn is immense. Saturn's mass is about 95 times that of Earth, and its gravity is 1.07 times stronger than Earth's at the equator. This gravitational force would extend far into the surrounding water, potentially causing enormous tidal forces. The sheer size and weight of Saturn would dominate any body of water large enough to float it, and the water would likely behave very differently from what we would experience on Earth. But while the idea of Saturn floating in water is fun to imagine, it also serves as a thought experiment to explore what makes Saturn so unique in terms of its physical characteristics. Its low density is not just a quirk but a vital part of its overall composition and behavior. The presence of lighter elements like hydrogen and helium means that Saturn is, in many ways, an outlier in the solar system. It is not a terrestrial planet, like Earth, that relies on silicate and metal cores. Instead, its massive size and gaseous nature create an environment that is far different from any of the rocky planets that surround it. the fact that Saturn could theoretically float brings us back to some fundamental questions about the nature of planets and the forces at play in the universe. What does it mean for a planet to be dense or light? How do the components of a planet interact to determine its size, composition, and behavior? And what can we learn from studying planets like Saturn about the broader mechanics of planetary formation and evolution? In the case of Saturn, its density tells us a great deal about where it formed in the early solar system. Gas giants like Saturn are thought to have formed further from the Sun, where temperatures were low enough for light gases like hydrogen and helium to accumulate. In contrast, the inner planets, Mercury, Venus, Earth, and Mars, are rockier because the heat from the Sun prevented lighter gases from condensing. This difference in composition is one of the key reasons Saturn has such a low density compared to Earth, and it reflects the different processes that govern the formation of planets in the outer regions of the solar system. To take the analogy further, we could think about Saturn's low density as a clue to its evolutionary history. The planet's atmosphere, made up largely of hydrogen and helium, gives us insight into the conditions that existed in the outer solar system when Saturn began to form. The lighter elements that dominate Saturn's structure are remnants of the early solar nebula, the gas and dust cloud from which the Sun and planets formed. As Saturn formed, it captured massive amounts of these gases, building up its atmosphere over millions of years. But while Saturn's low density may seem like an anomaly in the context of Earth's more solid, rocky composition, it is part of a larger pattern in the solar system. Gas giants like Saturn are not unique in their density. Jupiter, Uranus, and Neptune share similar characteristics. However, Saturn's combination of size, low density, and fascinating atmospheric composition makes it one of the most intriguing objects in the solar system. And though the idea of Saturn floating in a bath may be impractical in the extreme, it serves as an intriguing gateway to understanding the fundamental forces that shape our universe. The concept of Saturn floating in water invites further exploration of the forces at play in the universe and the unique characteristics of gas giants like Saturn. While the idea of placing a planet as massive as Saturn in a bathtub is purely hypothetical, it opens up a deeper understanding of planetary physics, including the relationships between a planet's mass, size, density, and the gravitational forces that govern their behavior. These characteristics not only shape the planet itself but also influence its interaction with the rest of the solar system. A key factor in understanding why Saturn could float is its overall composition. As we mentioned earlier, Saturn's low density is primarily due to its gaseous composition, consisting largely of hydrogen and helium. These elements are so light that they contribute to a relatively weak gravitational pull, compared to rocky planets like Earth. In contrast, Earth, with its dense, rocky interior, exerts a strong gravitational force. The dense materials that make up Earth's core are much heavier than the lighter gases found in Saturn's atmosphere, which leads to a substantial difference in how each planet interacts with its surroundings. Saturn's composition also has a significant impact on its internal structure and its behavior over time. Unlike rocky planets, Saturn lacks a solid surface, and its core is composed of ice, rock, and metal, surrounded by layers of hydrogen and helium. The gaseous layers are extremely thick, and as you move deeper into the planet, the pressure and temperature increase significantly. While the outer layers are relatively low in density, the core is much denser, with scientists estimating that Saturn's core is about 10 to 20 times the mass of Earth, despite its overall low density. This unique combination of a light outer atmosphere and a dense core creates a planet that, despite its large size and mass, behaves differently from terrestrial planets in terms of gravitational effects, buoyancy, and planetary formation. One of the most intriguing aspects of Saturn's low density is its potential for comparison with other gas giants in the solar system. For example, Jupiter, the largest planet in the solar system, has a higher density than Saturn, but it is still a gas giant. While Saturn's density is approximately 0.687 grams per cubic centimeter, Jupiter's is around 1.33 grams per cubic centimeter, which is still less than water's density. However, Jupiter's greater mass and size mean that it exerts a significantly stronger gravitational pull than Saturn, which leads to a different set of dynamic behaviors within the planet itself and in its surrounding environment. if we consider the difference between Saturn and Jupiter, it's important to recognize that their differences in density have a direct relationship with their respective formation processes. Both planets are believed to have formed in the outer regions of the solar system, beyond the frost line, where temperatures were low enough for hydrogen and helium to condense and form gas giants. However, Saturn likely had less material to draw on during its formation than Jupiter, which could explain its lower density. Saturn's smaller mass and the resulting lower pressure in its interior might account for the differences in the way their atmospheres and cores have developed. This disparity further emphasizes the relationship between a planet's size, its ability to retain gas, and the physical forces that dictate its overall structure. In addition to its internal composition, Saturn's mass plays a crucial role in its ability to influence the surrounding space environment. Saturn's mass is about 95 times that of Earth, and its strong gravitational field affects the orbits of its many moons, as well as the behavior of objects in the surrounding region of the solar system. Saturn's moons, like Titan, Enceladus, and Rhea, are subject to this powerful gravitational pull, which governs their orbits and contributes to the dynamics of Saturn's ring system. This force also extends to nearby asteroids and comets, altering their trajectories as they pass through Saturn's vicinity. Saturn's mass and gravity help maintain the integrity of its rings, which are composed of countless particles of ice, rock, and dust. These rings, which appear so delicate from a distance, are held in place by Saturn's gravitational pull, preventing the individual particles from dispersing into space. Despite Saturn's relatively low density, its gravitational influence is vast and extends far beyond the planet itself. In fact, Saturn's strong gravitational field plays a crucial role in shaping the solar system's architecture. The gas giant's position and gravity likely help to prevent the outward migration of icy bodies and comets, which might otherwise have drifted too far from the Sun. This process helped maintain the stable configuration of the solar system, where the inner rocky planets remain relatively close to the Sun and the outer gas giants, like Saturn, reside farther out. The relationship between Saturn's gravity and its moon system also offers insight into the nature of satellite formation and the unique characteristics of Saturn's moons. Titan, Saturn's largest moon, is one of the most intriguing bodies in the solar system. Titan has an atmosphere thicker than Earth's and a surface marked by vast lakes and seas of liquid methane. Titan's atmosphere and the presence of organic chemicals on its surface have made it a prime candidate for studies on the potential for life beyond Earth. The influence of Saturn's gravity on Titan and other moons is significant in the shaping of their features and the potential for future exploration. The idea of Saturn floating in water also brings to mind the complex behavior of gas giants in our solar system. Unlike terrestrial planets like Earth, gas giants like Saturn have no solid surface, making them fundamentally different in how they interact with the environment. The outer layers of gas giants are not rigid like the solid surface of Earth, and this allows for a greater degree of fluidity and flexibility in their behavior. As gas giants, Saturn and its companions are subject to forces that we don't typically encounter on rocky planets, including strong planetary winds, extreme atmospheric pressures, and intense magnetic fields. One of the most notable aspects of Saturn's atmosphere is its storm activity. The planet is home to the famous Great White Spot, a massive storm that occurs roughly once every Saturnian year. These storms can reach up to 1,000 miles per hour and have been studied extensively to understand the dynamics of weather on gas giants. Saturn's atmosphere also features distinct banding, with alternating light and dark clouds that create striking visual patterns. The way Saturn's atmosphere behaves under the influence of its low density, combined with the planet's rapid rotation, contributes to the dramatic weather phenomena that define the planet's appearance. The extreme nature of Saturn's atmosphere, combined with its low density, highlights the stark contrast between gas giants and rocky planets like Earth. Gas giants like Saturn represent a category of planets that are far less understood in many ways, primarily due to their lack of a solid surface and their vast, dynamic atmospheres. However, the more we learn about these planets, the clearer it becomes that their behavior, while very different from Earth's, offers critical insights into the processes of planetary formation and the diversity of conditions that exist in our solar system and beyond. In considering Saturn's potential to float in water, we are reminded of the broader cosmic context in which this hypothetical scenario exists. The planet's low density and gaseous composition are just a few of the factors that make Saturn so unique in the solar system. From its role in shaping the structure of the solar system to its vast array of moons and extreme weather, Saturn offers an exciting window into the complexities of planetary science. While the idea of floating Saturn in a bathtub is impossible in practice, it invites us to think about the forces that shape our universe and the dynamic interactions that make each planet a unique and fascinating entity. Building on the understanding of Saturn's composition and its unique low density, we can delve deeper into the broader implications of Saturn's physical characteristics and how they challenge traditional ideas of what planets are and how they behave. While the whimsical notion of Saturn floating in a bathtub is a fun thought experiment, it also leads to a more serious exploration of the diverse ways in which planets form, interact with their environments, and evolve over time. This exploration is crucial not only for understanding Saturn itself but for shedding light on the nature of planetary science as a whole, particularly in the study of gas giants and their role in the solar system. To appreciate Saturn's place within the solar system, it's essential to look at how gas giants like Saturn are formed and how they compare to other types of planets, especially the rocky planets like Earth, Venus, and Mars. The prevailing theory of planet formation suggests that gas giants like Saturn form in the outer regions of the solar system, beyond the frost line, where temperatures are low enough for light elements like hydrogen and helium to condense. In contrast, the inner planets, where the temperatures were higher, are predominantly composed of heavier elements such as metals and silicates. This fundamental difference in composition is key to understanding why Saturn, despite its enormous size and mass, is less dense than Earth and the other terrestrial planets. The frosty outer regions of the solar system, where gas giants form, are ideal environments for the accumulation of hydrogen and helium, the most abundant elements in the universe. These gases condense into a thick atmosphere that surrounds a small, rocky core. Over time, the accumulation of these gases, combined with the planet's own gravity, allows the gas giant to grow to enormous sizes. Saturn, for instance, has a radius of about 9 times that of Earth and a mass that is approximately 95 times greater. However, despite its mass, the relatively low density of its composition means that it is less compact and, as we've seen, capable of floating in water. If such a hypothetical scenario were to exist, this contrast between the gas giants and the terrestrial planets becomes even more apparent when we consider the way gravity works on each. In the case of gas giants like Saturn, the gravitational pull is distributed more evenly across the planet's enormous atmosphere, which contributes to the planet's relative lightness. On the other hand, Earth's gravity is concentrated in a smaller, denser volume due to the planet's rocky composition. This difference in gravitational distribution has important implications for the way planets evolve over time. For example, the outer gas giants like Saturn and Jupiter have retained most of their original gas envelopes, while the inner, rocky planets lost much of their lighter elements during the early stages of the solar system's formation. Saturn's position in the solar system also plays a crucial role in shaping its behavior and its relationship with the rest of the solar system's planets and moons. Saturn is located in the outer part of the solar system, where the gravitational influence of the Sun is weaker than in the inner regions. This makes Saturn's massive size and gravitational pull particularly significant for the orbits of its moons and even the behavior of comets and asteroids that come too close. Saturn's gravity helps maintain the structure of its famous ring system and prevents objects in its vicinity from drifting too far away. Its gravitational influence extends far beyond the planet itself, affecting the trajectories of nearby bodies and contributing to the general architecture of the solar system. Moreover, Saturn's moons play a key role in the planet's dynamics, providing a wealth of scientific interest for astronomers. Titan, Saturn's largest moon, is of particular interest due to its dense atmosphere, which is primarily composed of nitrogen, methane, and hydrogen. This thick atmosphere, combined with the presence of liquid methane lakes and seas on the Moon's surface, makes Titan one of the most Earth-like places in the solar system in terms of its surface features. Titan is also a key object in the search for life beyond Earth, as its environment might offer clues about how life could potentially arise in conditions very different from those on Earth. The study of Saturn's moons, and Titan in particular, is vital for expanding our understanding of how planetary environments evolve and what conditions might foster the development of life. In contrast to Titan, some of Saturn's other moons, like Enceladus, have been the subject of intense scientific scrutiny due to the discovery of geysers shooting water vapor and organic molecules into space. This has led to the hypothesis that Enceladus may harbor subsurface oceans, which could potentially support microbial life. The discovery of liquid water beneath the icy surface of Enceladus suggests that Saturn's moons may hold more secrets about the potential for life in the outer solar system than previously thought. These discoveries are reshaping our understanding of what makes a planet or moon capable of supporting life, and they underscore the importance of studying gas giants like Saturn, not just for their own unique properties but for what they reveal about the broader cosmos. Saturn's low density and its status as a gas giant also contribute to its fascinating atmospheric dynamics. The planet's atmosphere is subject to extreme winds and storms, including the famous Great White Spot, a recurring storm system that occurs roughly every 30 years. These massive storms, which can span thousands of kilometers, are some of the most powerful weather systems in the solar system. Saturn's rapid rotation, the planet completes one rotation in just under 10.7 hours, further contributes to the extreme weather patterns, creating a turbulent and dynamic environment. Understanding these atmospheric systems is crucial not only for comprehending Saturn but also for gaining insights into the behavior of other gas giants, both in our solar system and beyond. As Saturn's atmosphere is primarily composed of hydrogen and helium, the planet does not exhibit the same surface features that we find on Earth. There are no solid continents or oceans, only swirling clouds of gas that vary in color and structure. The differences in cloud composition and color are thought to be caused by variations in temperature, pressure, and chemical composition within Saturn's atmosphere. The study of these atmospheric layers offers valuable clues about how gas giants form and evolve, as well as how they interact with their moons and other bodies in the solar system. Despite its extreme distance from Earth, Saturn has had a profound impact on our understanding of planetary science. Missions like NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, have provided a wealth of data about the planet and its moons. The insights gained from these missions have helped scientists refine models of planetary formation, atmospheric dynamics, and the potential for life beyond Earth. Saturn's unique characteristics, from its low density to its dynamic atmosphere and fascinating moons, continue to challenge our understanding of planetary systems and offer new avenues for scientific discovery. In conclusion, Saturn's low density and its potential to float in water serve as entry points into a larger conversation about the unique nature of gas giants. Saturn's composition, gravitational influence, and atmospheric dynamics differentiate it from the inner, rocky planets of the solar system and offer a window into the diverse processes that govern planetary formation and evolution. While Saturn may never truly float in a bathtub, the principles behind this hypothetical scenario serve as a fascinating lens through which to explore the nature of the planets, their formation, and their role in the broader cosmic context. Through the study of Saturn and its moons, we are not only gaining insights into the behavior of gas giants but also expanding our understanding of the universe and the potential for life beyond Earth. Continuing from the understanding of Saturn's physical characteristics and its dynamic role within the solar system, it is crucial to explore how Saturn's low density and composition influence its interactions with other celestial bodies, particularly in relation to the broader dynamics of planetary formation and evolution. While Saturn's ability to float in water remains a theoretical scenario, the implications of its low density are far-reaching, affecting not just the planet itself but also its moons, rings, and the surrounding space environment. one of the most significant factors in understanding Saturn's role in the solar system is its gravitational influence. As the second largest planet in the solar system, Saturn exerts a massive gravitational pull on nearby objects. This influence plays a key role in shaping the orbits of its moons and maintaining the structure of its extensive ring system. Saturn's gravity helps to stabilize the orbits of its moons, preventing them from drifting away into space. The gravity of Saturn also interacts with the other gas giants, particularly Jupiter, to influence the paths of asteroids and comets that come close to the planet. This gravitational relationship among the gas giants is a critical factor in the overall stability and configuration of the solar system. The study of Saturn's rings is an essential aspect of understanding its influence within the solar system. Saturn's rings are composed of countless particles of ice, rock, and dust, each ranging in size from tiny grains to large chunks. These particles are primarily made of water ice, which reflects sunlight, giving Saturn's rings their bright, reflective appearance. The rings are not solid but rather consist of millions of individual objects that orbit Saturn in a thin, flat plane. Despite the appearance of a unified structure, the rings are constantly shifting and evolving, with particles colliding and redistributing over time. Saturn's gravity plays a significant role in maintaining the ring structure, and scientists believe that the rings themselves may have formed relatively recently in the planet's history, possibly from the remains of a moon or comet that was torn apart by Saturn's tidal forces. In addition to shaping its own ring system, Saturn's gravitational influence extends to the behavior of comets and asteroids in the outer reaches of the solar system. Saturn's massive size and strong gravitational field make it an important player in the dynamics of the Kuiper Belt and the Oort cloud, two regions that are home to a large number of icy bodies and potential comets. The gravity of Saturn, along with Jupiter's, helps to shape the trajectories of these objects, sometimes sending them on paths that bring them closer to the inner solar system. This gravitational influence is one of the reasons why gas giants like Saturn are often referred to as vacuum cleaners of the solar system, as they help to prevent comets and asteroids from colliding with the inner planets by redirecting them away from the Sun. Saturn's relationship with its moons is also an important area of study. The planet has more than 80 known moons, many of which are quite intriguing due to their unique characteristics. Titan, Saturn's largest moon, is of particular interest to scientists due to its thick, nitrogen-rich atmosphere and the presence of liquid methane and ethane lakes on its surface. Titan's atmosphere is one of the most Earth-like in the solar system, and its surface conditions are similar to those of early Earth. Titan's large size, combined with its thick atmosphere, has made it a prime candidate for exploration in the search for life beyond Earth. The Cassini-Huygens mission, which studied Saturn and its moons, sent the Huygens probe to Titan's surface in 2005, providing the first direct images of the moon's surface and atmosphere. This data has been crucial in advancing our understanding of the moon and its potential for harboring life or lifelike processes beyond Titan. Saturn's other moons, such as Enceladus, Rhea, and Mimas, each present their own mysteries. Enceladus, for instance, has been found to have geysers that shoot water vapor and organic molecules into space, suggesting the presence of a subsurface ocean beneath its icy crust. This discovery has sparked interest in the possibility that Enceladus, like Titan, could potentially harbor microbial life in its hidden oceans. The geysers of Enceladus are thought to be powered by tidal heating caused by the gravitational interaction between Enceladus and Saturn. This process, known as tidal flexing, generates enough internal heat to keep the moon's subsurface ocean liquid, creating an environment that could support life in a way similar to how life might have formed in Earth's deep oceans. Saturn's moons, with their diverse environments and potential for habitability, challenge our understanding of what constitutes a habitable environment. While Earth's surface conditions, liquid water, an oxygen-rich atmosphere, and moderate temperatures, are often considered necessary for life, moons like Titan and Enceladus demonstrate that life could potentially exist under very different conditions. These moons offer unique opportunities for scientists to study the conditions that might support life beyond Earth, expanding our understanding of where and how life might arise elsewhere in the universe. Saturn's low density also has profound implications for its long-term evolution. Unlike Earth, where the internal pressure and temperature have driven the differentiation of layers, Saturn's low density and gaseous composition mean that the planet has not undergone the same type of differentiation. While Earth's inner core is composed of dense metals like iron and nickel, Saturn's core, although believed to be made of rock and ice, remains less defined due to the planet's gaseous outer layers. Over time, Saturn's core may continue to contract, but the overall structure of the planet will remain dominated by its thick atmosphere and the ongoing balance between the forces of gravity, pressure, and temperature. The future of Saturn's rings and moons is another important consideration. As we've seen, Saturn's rings are constantly changing due to the gravitational interactions between the particles in the rings and Saturn's moons. Some of the particles in the rings are believed to be slowly spiraling inward toward the planet, while others are being ejected into space. This ongoing evolution of the ring suggests that they may not be permanent structures, they could eventually dissipate or merge with Saturn's atmosphere over the course of millions of years. Similarly, the moons of Saturn, especially those that show signs of subsurface oceans or active geology, will continue to be of significant interest in the study of planetary science. Saturn's role in the broader context of planetary science goes beyond its immediate surroundings. The planet and its moons offer key insights into the processes of planetary formation, the potential for life in extreme environments, and the dynamics of the outer solar system. Understanding Saturn's structure, its moons, and its rings helps scientists to build models of other exoplanetary systems, as gas giants and moons are often among the most common types of planets discovered in distant star systems. The study of Saturn, as one of the best-studied gas giants, provides valuable context for understanding the wide variety of planetary systems that exist in our galaxy and the possibilities for life beyond our own solar system. In sum, Saturn's low density, its influence on its moons and the solar system's dynamics, and the unique characteristics of its atmosphere, rings, and moons make it one of the most fascinating objects in the solar system. The study of Saturn not only deepens our understanding of gas giants and planetary formation but also provides valuable clues about the potential for life on other worlds. Through ongoing exploration and research, Saturn continues to reveal its secrets, offering a wealth of knowledge about the nature of planets, moons, and the broader universe. While the idea of Saturn floating in a bathtub may remain purely hypothetical, the deeper scientific questions it raises about the nature of planetary systems are both profound and transformative.